Before I go ahead with this example, I suggest that you pause the video and read the text and see if you can come up with the schematic for this example, and even better, if you can actually come up with a circuit related to the schematic, and then unpause the video. Now I'm assuming you've unpaused the video, so let's see what the example is about. Consider an air heater consisting of a semi-circular tube for which the plane surface is maintained at 1000 degrees Kelvin, that would be the heater surface, and the other surface is well insulated, which means that no heat will go through it. The tube radius is 20 millimeters, and both surfaces have an emissivity of 0.8. This is just some information I'll need later for my radiation calculations. And then, if atmospheric air flows through the tube at 0.01 kilogram per second and at mean temperature of 400 degrees Kelvin, what is the rate at which heat must be supplied per unit length to maintain the plane surface at 1000 degrees Kelvin? So now I know that there's air flowing between the two surfaces, so it's not just a radiation case, there's actually a flow of air, which means that I do have convection as well. So when I'm looking at surface 1, which is my heater, I'm not only radiating heat off from the surface to the surrounding, I'm also convecting heat out. So heat is going to go from node 1, or the node for surface 1. It's not only going to be radiated towards the other surface, but it's also going to be convected. And that's what I'm going to assume on the bottom surface based on this information. So if this was a radiation case, we said that you start with your two nodes, J1 and your J2, and those two have some view factor towards one another, and there's a geometrical resistance between these two, and that is your 1 over A1F1. That is already decided. Now, before J1 and after J2, you have two more resistances for radiation if your surfaces are not black body surfaces, which are not. In our cases, both of our surfaces have an emissivity of 0.8. It's already saying that it's not black body. So I'm going to have two more resistances, which is this one on the left and this one on the right. And then I get to the nodes EB1 and EB2. Now I want to see what happens here. On EB1, which is my heater surface, I get some heat input externally. I'm using some whatever electrical power, whatever I'm using in order to provide heat on the surface 1. That's my heater surface. And then I know that some of that goes towards surface 2 by radiation, and some of that is going to be convected. As we said in the multi-mode slide, we are going to put that heat on this node, on the EB node. Anything after that, the radiosity nodes, are just for the radiation from one surface to another. So now I'm putting this convection here. So I know that there's convection from surface 1 to the air, but how about surface 2? So if surface 1 is sitting at 1000 degrees Kelvin and the air is at 400 degrees Kelvin, unless my surface 2 is at 400 degrees Kelvin, there is going to be convection heat transfer from surface 2 to the air as well. So it's not just the heater that is losing heat to the air through convection, it's also the semicircular tube side as well, the curvy side of this tube as well. So then I know that on the other node, surface 2, I'm also going to have some convection heat transfer. And that does make sense to me in a way, because the radiation from surface 1 to 2 can't pass through surface 2. It has to go somewhere. If it doesn't really find a way to go to the air or anywhere else, then that surface temperature is not going to maintain its temperature. Its temperature is going to keep going up because it's just receiving heat through radiation from another surface, and then it's not really letting it go through any mode of heat transfer. So because we've said that it's insulated, that means that this heat here is going to be zero. There is not going to be any passing through the surface, so the only way that this heat can escape surface 2 is going to be through convection. And that's how we set up our circuit. So in our circuit, we have radiation between surface 1 and 2, but then on the two surfaces, we're also assuming that there's convection heat transfer. So now I need to calculate the external heat that enters the circuit in order to see how much heat I need to provide to the heater in order for it to remain at 1000 degrees Kelvin. And when I look at my circuit, I see that part of this heat is going to be directly convected to the air, and then the other part is going to be radiated to the other surface, which will then be convected to the air. So it will be basically two convection heat transfer modes. So I will say that the Q1 external from the external source is going to be Q that's convected from surface 1 plus Q that's convected from surface 2. I mean, that's what eventually will happen with surface 2. I could also say that this is Q convection 1 plus, I could also say this, Q convection 1 plus Q 1, 2. I mean, it's the same amount of heat that gets to the surface 2 and then gets convected out. And this is through radiation. But I prefer to use this. So now I'm going to say, from there, I can say that Q1 external, I'm going to expand convection 1 and convection 2. Well, if you remember from before, convection heat transfer would be H bar, area 1, T1 minus the temperature of the air, and then convection from surface 2 would be H bar, and I'm assuming that they're same H bars because it's the same flow. Both surfaces are seeing the same flow. So that would be H bar and A2 T2 minus Tm. There is a little bit of difference in calculation of H bar from surface 1 to the air versus surface 2 to the air. I know that the temperatures of those two surfaces are not the same, so the film temperature is going to be a little bit different, and as a result my properties are going to be a little bit different, but then I don't have the temperature for surface 2. So for now I'm going to assume that it's the same film temperature, and I'm just going to assume that the temperature of the mean temperature of the air is the temperature that I'm going to pick my properties, and I'll use those properties for now, just for simplification. I'll use those properties for now in order to calculate the H value. But is that only the H value that I'm looking for? There's also T1 and Tm. Tm I know is 400 degrees Kelvin. T1 I know is at 1000 degrees Kelvin, and T2 is something that I don't know. That's actually something else that this question is asking. So my unknowns are the T2 and the H bars here. So now I'm going to calculate H bars first, and then I'll go to calculate T2, and then I'll come back to this relation to basically put all this here to calculate what the total heat is in order to maintain the surface temperature at 1000 degrees Kelvin. So I have to figure out what type of convection heat transfer I have here. I have free convection heat transfer or forced convection heat transfer. I would say that this is forced convection heat transfer because I'm forcing flow inside this duct. So among the forced convection heat transfer options, I have forced convection in external surfaces or internal forced convection. External forced convection would be a flow over a surface where your boundary layer could grow, and then it would become a turbulent flow, all of that. And then your internal flow convection would be, and that would still be forced, would be flow in a tube, in a duct, where your flow is contained within the walls of that tube. This is a case for internal flow convection. So in both of the cases, forced flow, I do have to calculate my Reynolds number. So to see if it's a laminar flow or a turbulent flow. So for laminar flow, I will have to write rho v for the velocity, and then I have this dh, which is the diameter for cases where you have a tube or a duct that is not that does not have a circular cross section. So in a case like this, I don't have a circular cross section. I have to come up with a kind of an equivalent diameter for the cross section. So I'll have to first figure that out before I actually do anything with this Reynolds number. So let's just figure that out first. The dh, the definition for that would be 4 times the area of your cross section divided by the perimeter of your surface. So 4 times area of my cross section is pi r squared is the area of a full circle. So pi r o squared divided by 2 would be the area of this cross section, which is half of a circle. And then the perimeter would be 2RO plus the half circle perimeter would be, again, 2 pi r would be the perimeter of a full circle. Pi r would be the, pi r would be the perimeter of a circular, of a half circle. Then I'll just have to substitute the values here. So that's 4 pi. If I substitute RO, that would be 0.020 to the power 2 divided by 2. 2.020, that's my R0, plus pi 0.020. Now I have my dH calculated as dH 0.0244. And this is basically the characteristic diameter that I use in all my relations here and in my Nusselt number. So now I go back to my Reynolds number. When I'm looking at my Reynolds number, I have a velocity and the numerator v. I can go calculate that, or I can just try to see if I can turn this into m dot. I know that m dot is rho v a, right? Area of your cross section. So I'm going to, let's just call it area of cross section. So I'm going to try to see if I have that in my numerator. I have rho v, I don't have an a. I'm going to multiply both the numerator and the denominator by an ac to just create what I want. And I am allowed to do that because I'm multiplying it by both sides. So mu and then ac. Now the top side, this becomes my m dot. So now I have m dot dH mu, and then AC would be actually the area of my cross section, which is pi RO squared divided by 2 because it's a half circle. So now this is my new formula for my Reynolds number. Now I'll just have to substitute the values. 0.01 for m dot. dH I just calculated it to be 0.0244. Then I'll divide that by mu. I've got that from the table at 230 10 to the negative 7. Note here that I've used 400 degrees Kelvin as the temperature that I use for getting values from the table. And the reason is I don't have any better estimate for now. Then I have my mu. What else do I need? Pi 0.020 divided by 2. This is all the values going in, and that should give me my Reynolds to be 16,912, which is much larger than 2300, which means that this is a turbulent flow. Now, because I have a turbulent flow, and the reason I actually went through all this, it was to figure out what type of flow I have, because I have so many different Nusselt number relations, and I need to figure out which one to pick. So I go and pick up the Nusselt number, the one that we usually use for turbulent flows in cases of internal forced convection, which is 0.023, your Reynolds number to the power 4/5, and your Prandtl number in this case would be 0.4. So now I'll just have to substitute the values. And by the way, Nusselt's number was your h dH divided by your k. So now I'm actually going, and that's going to be my Nusselt's number, which is actually all those values. So I'm going to substitute h. I'm going to put my dH as 0.0244. I divide by the conductivity of the air, which I've picked up, should have picked up from the table, 0.0338. And that should be equal to 0.023, and your Reynolds, which is at 16,912 to the power 4 divided by 5. And your Prandtl number, which is supposed to be at 0.69 divided by 0.4, to the power 0.4. And that should give me H equal to 66.2 watts per meter square Kelvin. If you remember in the previous slide, we needed H and we also needed a temperature, but this is the H, and actually this is H bar. This is Nusselt bar, this is H bar, and H bar here, and the Nusselt bar here. So this is the H bar, or the convection heat transfer coefficient, that I can use in the relation in the previous slide. Okay, now I have to calculate the external heat from here. In order to calculate that, I need to calculate my temperature on the surface 2 as well. So in order to calculate temperature on surface 2, I know that it shows up here in this point, Stefan-Boltzmann constant T2 to the power 4. So I'll be able to write a relation that has that note in it. One thing I can say is that the radiation that goes from surface 1 all the way to surface 2 is going to be equal to what is going to be convected to the air, because there's no other way for heat to go at that point. At surface 2, heat will arrive there by radiation, but then it will have to be lost to the air. So I can say that Q radiation from 1 to 2 is going to be equal to Q convection from surface 2. Q radiation from 1 to 2, the net radiation from 1 to 2 is going to be written as, you have the circuit, so you pick any two nodes, well, not any two nodes, nodes that will be helpful. For example, I'll pick EB1 minus EB2, because I know I can at least evaluate EB1, and then I'll find the resistances in between these two nodes. So that's 1 minus epsilon 1 A1 plus 1 over A1 F12 plus 1 minus epsilon 2 A2. So that will be my left-hand side, and the right-hand side I know it's convection on the second surface. Convection on the second surface will be H bar, it's convection A2, temperature of the second surface minus temperature of the air. That would be the formula for convection heat transfer. The EB values, in order to evaluate them, you have to have your Stefan-Boltzmann constant T to the power 4. So that's Stefan-Boltzmann constant T2 to the power 4. Looking at these two relations, the only unknowns that I have is T2 and F12. The rest, I already have them or can calculate them. F12, I can take care of that by writing F11 plus F12 is equal to 1. The portion of radiation that can see or that can arrive on another surface plus the portion of radiation that can arrive on itself should be equal to 1. And because we know that surface 1 is a flat plate, it doesn't see itself. So F11 is going to be 0. It doesn't view itself. So then F12 is going to be 1. So now I only have one unknown in this relation. If I substitute the values in the rest of the relation, I should be able to get my T2 from here. So let's get started on that. 5.67 10 to the negative 8, and I'll factorize the Stefan-Boltzmann constant. I'll put my temperature divided by 1 minus 0.8, 0.8 for emissivity. For area 1, I need to know my area. My area is going to be 20 millimeters on this side and 20 millimeters on this side, so that's going to be 40 millimeters, 0.040. That's only the width. I know that this is a duct that goes up to a length. I'll call that L, and I'll multiply this L here as well because that will be my area. Plus 1 over, again I have 0.040 L as my area 1, and I said F12 is 1. Plus 1 minus 0.8 divided by emissivity 2 is emissivity 2 is also 0.8, and my area 2 is the area of the perimeter of half circle multiplied by L. So the perimeter of full circle is 2 pi r. Pi r is going to be the perimeter of half circle multiplied by L. Oh, yeah. So now on the right hand side, I'll be able to say my H bar from the previous slide is 66.2. My area is going to be the same way that I calculated just now, pi 0.020 L. And then what else do I have? T2 minus Tm. T2 I don't know, I'm looking to calculate that. Tm is 400 degrees Kelvin. So now this relation, it's not very easy to calculate the T2 from this relation, because on the one side your T2 is to the power 4 and on the other is to the power 1. If your calculator does that, you could use your calculator for this. If you're sitting at home doing this, you could always use Excel. If it's in real engineering firms, you can definitely use tools to calculate that. If this is an exam, you could make an assumption and see if both sides of the relation work. So kind of like a trial and error method to see if you get close enough to T2, or if you can actually solve this type of relation. So if you actually try to solve this, you should be able to arrive at T2 at 696 degrees Kelvin. So now I'm back at my original slide at the very beginning of solving this problem, and I said at that time that H bar and T2 were the unknowns, and I've already calculated those. So now I'm going to calculate my Q1 external as my H bar. So my H bar is 66.2. A1 is, I said that A1 was 2 R's, so 2 by 0.020 multiplied by L, and then T1 was 1000 minus 400 plus 66.2. A2 was pi RL, pi 0.020. If you remember, 2 pi r is the perimeter of a circle, pi r is the perimeter of a half circle, and the perimeter of a half circle multiplied by the length of the tube is your area. So that's pi RL, and then we have T2, which we calculated to be 696 degrees Kelvin minus 400, and this should give me Q1. The heat needed in order to keep this surface at 1000 degrees Kelvin is going to be 2820 L. And this will be in watts. What we were interested to calculate was actually Q prime 1 external. That's my Q1 external heat divided by the length of the duct, which is 2820 L divided by L, which is going to be 2820 now watts per meter. This is how much heat you have to provide, how much heat or electrical power you have to provide to the surface 1 in order to maintain it at 1000 degrees Kelvin.